Hello, my name is Marlene Gonzalez. I am presenting my poster entitled Electrochemical Deposition of Nanolayer of Iron-3 Oxide on Silicon. As an introduction, this project came from the interest in growing an ultra-thin film of pure iron oxide on silicon to learn about the physical origin of the Shirley background. Previously, we found that iron-3 oxide, or hematite, is the easiest and the most stable oxide to obtain. However, with the sputtering deposition, some pure metallic iron and other suboxides remain after low temperature annealing. On the other hand, higher temperature annealing causes a chemical reaction with silicon and the formation of protrusions. To overcome this problem, we propose to make hematite nanofilms using electrochemical deposition, providing a convenient way to synthesize films and control the thickness in relation to the deposition cycle. In addition, it is a low-cost option that grants uniform large area deposits, and it can be performed at room temperature. For the deposition process, it was used an aqueous solution of iron-3 chloride in a 3-electrode cell with the silicon substrate as the working electrode, a saturated calomel electrode as the reference, and platinum as the counter electrode. The potential soot rate was fixed to 20 millivolts per second with a potential window from -900 to 0 millivolts versus the calomel electrode. Finally, the obtained films were annealed at 200 Celsius degrees in an ambient atmosphere for 2 hours. To gain an insight into the oxidation states and surface chemical composition after 800 cycles, XPS measurements were carried out. Figure 2 shows the surface chem spectrum showing only iron, carbon, and oxygen in the film, suggesting a pure oxide deposition. To corroborate this hypothesis, high-resolution XPS analysis was conducted and fitted using analyzer software. Peak fitting was used to determine peak center and widths. A combination of Shirley-Selby Castle and slope background were considered for background. The main iron peak had a double Lorentzian form. Its characteristic spin orbit splitting and binding energy position, along with the fact that only one oxygen peak is bonded to it, demonstrate the presence of iron-3 oxide as the only phase in the film. The carbon peak came from adsorbed atmospheric hydrocarbons. It was fitted with 3 void singles, with the most intense bonded to oxygen and the others attributed to sp2 and sp3 hybridizations. After conducting the experiment, the relationship between the number of cycles and the width of the film was analyzed. The results, as shown in Figure 3D, indicate that a lower number of cycles lead to a decrease in peak intensity. Because the fitted spectra show the same numbers of decumulated peaks, the film only presents a thinner pure iron-3 oxide deposition. Electrochemical deposition is regarded as a simple and powerful method for making pure thin metallic films. The XPS spectra could be fitted using analyzer software, reproducing the experimental data with double Lorentzian forms and Shirley-Selby Castle and slope backgrounds. Thank you for watching.